Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will have the opportunity to access it later on. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for our speaker, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your questions. And we will try to get to as many as we can near the end of today's webinar. Also, at the end of today's webinar, we will be doing a drawing for four $100 Amazon gift cards. So please stick around. Hopefully you'll be one of our 4 lucky winners. All right, with that, let's go ahead and kick off today's webinar, which is Akka Cluster and Red Hat OpenShift, a symbiotic relationship. Our speaker today is Hugh McKee. Let me introduce you, Hugh, who is the developer advocate at Lightbend. And now I'm going to let you take it away, Hugh.
All right, thanks a lot. Hello, everyone. Really appreciate you being here today. When I was doing the slide deck, the term symbiotic relationship, really, I think right away of the clownfish and the sea anemone. This is like the classic symbiotic relationship in nature. But as I'm going through this presentation, I'll be kind of introducing you to Akka clusters, which is something that we provide at Lightbend, and kind of going over some history. But there is really, truly a symbiotic relationship between these two. I've been using Akka before I became aware of things like Kubernetes and OpenShift, and we needed an orchestration layer like what we're getting with OpenShift. So it's a very cool relationship, and that's what I hope to really get across to you. So to start out, I just want to go into a demo application right away and show you something. This is a demo app that I wrote, but it's kind of it's kind of an IoT-based application, and it's a map-based application. Now, I'm on pins and needles because this darn demo app has been acting up on me the last couple of days. So we'll see if I run into trouble or not. But I've got 2 demos actually I'll be showing you today. One is running on OpenShift and Kubernetes containers on my laptop. But this one I want to show you right now is actually running in the cloud. And it is this map-based type of IoT thing. So the goal of this demo application was to run in a clustered environment in the cloud, and it was really to exercise Akka, but also do things like exercise databases. So you can see that in this map, there's flags, markers distributed around the world, and this indicates where IoT devices, simulated IoT devices. There's not any real IoT devices out in the world, but I've got a simulator built into this demo application where I've created some IoT devices, and the devices have state. They can be happy, they can be sad. That's their state. So the idea is you can navigate around this map, kind of like a Google map, and you can zoom in an area. I'm going to zoom into one of my favorite areas around London. And as I get closer to the Earth, you can see that the markers give way to showing regions of the map where there are devices. So the idea with this demo app is that you can create a bunch of devices. You can create one device in some geographic region. You can create a bunch of devices with a single click and things like that. So again, it's really to exercise things. So I'm just going to do a quick demo though. But one of the things you can do with this is you can, I'm zoomed into a level where this region that's popping up, if I click it, it's going to send a request to some backend microservices. They're running in an OpenShift like environment and running in the cluster, and I'll show that in a little bit. But it's going to trigger the creation of 1,024 IoT devices. So I'm holding our breath. I'm going to click and see if anything happens. It was working before I started. This darn thing. Oh, well, now I'm getting off to a great start. I'll try and have to adapt. What should have happened, I'm sorry, but this, like I said, this darn thing has been acting up on me. It did it to me yesterday in another session. Been working all morning, but anyways, what would happen is that the region where I was asking to create some devices, what would happen was it would send in a single HTTP request to the backend system. The backend system would process that and then send in to another, from one service to another service, send in like 1,024 simultaneous telemetry messages, asking the second microservice to create a bunch of devices. And this triggers all kinds of database activity and things like that. And again, I really apologize because the darn thing is catching me at the worst possible moment, like right now. But anyways, I'll see if I can get it going as I'm going through this. Probably not, but because I probably have to restart it. But I got another demo app that I'll show you in a few minutes that we'll get into. But the whole point of this is that this is a Akka application running in a OpenShift environment, and it's taking advantage of this OpenShift environment. So the idea is that like with OpenShift, the way I look at it is that OpenShift, and I'm a developer, I'm an architect. So when I think about OpenShift, I really just think about it as a big place to run my stuff. And I kind of think about it as this two-dimensional area that on one axis, you've got CPU capacity, on another axis, you've got memory capacity. So my simplistic view of OpenShift and Kubernetes, it's just this environment where there's these nodes, machines that have CPU and memory capacity, and they form themselves into a cluster, which is managed by OpenShift and Kubernetes. And that this cluster is a place that has memory and CPU capacity. And then each of these nodes, and this is what the orchestration does within Kubernetes, of course, is running pods. And with each of the pods, we're running containers. And then within each of the containers, we're running processes. So here I'm just showing things like running Java processes, running JVMs, or maybe some Python or Node.js or whatever else you want to run in Kubernetes. This is the beauty of running things in environments like OpenShift, is that you have this orchestration layer. Now, when I was putting this slide together, it just made me think about the Russian dolls. The one doll is within another one, and that's pretty much this hierarchy of this relationship between an overall Kubernetes or OpenShift environment, which contains nodes. Nodes contain pods. Pods contain containers. And finally, within containers run processes, and that's where like my code runs, or your application code runs. So for Akka, the only real thing here is that some of these pods are running Java virtual machines, because Akka is written in Java or Scala, the Scala programming language. They're running just in pods, but they're running collaboratively, where they're forming a cluster. So in this view, this cluster view at the OpenShift level, I'm showing, say, two microservices, microservice 1 and microservice 2, with the different colors. And one microservice is running on 4 pods, and another microservice is running on 3 pods. So the way this works at the Akka level is that there's 2 microservices, say, and they run in a collection of pods, and these pods form themselves into a Akka cluster. So they locate each other running inside of Kubernetes through things like Kubernetes APIs and so on, and they find each other, and then they start communicating with each other over the network, and they start collaborating very tightly as a tightly coupled cluster. So it's really these clusters that are this tightly coupled collection of JVMs, which provide an environment which is a single distributed actor system. And I'll get into what an actor system is in just a bit, but basically for a developer, you write code as if you're running, that code's going to be running, say, in one process, but in reality, the code that the developer writes can actually run in multiple places, and they work together as if they're a single program, but that program's running across multiple pods within the environment. So as an example, this uncooperative demo app that I just tried to show you a moment ago, it's running with both of them are running the two services that are running with 6 pods. And this application I call it's WhereOnEarth, and just like I say, it's just a demo app that has 2 microservices. So there's a WhereOnEarth simulator and there's a WhereOnEarth twin. So the simulator service is the one I was saying earlier. It's the one that receives requests from the user interface to say, hey, create a bunch of devices, and then it pretends like it's the outside world. It's because I want to have a demo app where I can generate some traffic and some flow, but I don't want to have a real complicated environment for doing that. So I built this demo app so that other developers could take it, use it, set it up on their own environment, play with it, and things like that. So I wanted to have it be somewhat lightweight. So the simulator is the thing that generates traffic, and it's sending telemetry messages via gRPC over to the twin service, which is another microservice. And both of these services are written using Akka. The reason I use the term twin is Tesla is using Akka for some pretty cool apps. One of them is with their batteries. They're doing some pretty interesting things with that. And they did a talk last year at some conference, and they coined the term digital twin. And what they were talking about was that there's an actor for every physical device out in the real world. So, say there's a battery in somebody's home. On the back end system, there's say 1 or more actors that are allocated to that home, and another set of actors allocated to another home, and so on. So there's this kind of physical device out in the real world, virtual device, a digital twin back, running in the cloud. So a big thing with, for me, I'm a developer, but I've had some really interesting conversations in my career. I've been doing this for a long time, and also at conferences with DevOps folks. And, for DevOps, I think one of the big things is, running things in production, keeping them running in production, keeping the drama of running those things in production down to the least level, possible. Less drama, happier people, that type of thing. But I think another thing though is building systems that just kind of work. And there's this concept called reactive systems. And this is a pretty important to us at Lightbend. It's kind of the core of what we try and do. And reactive systems are pretty intuitive though. A reactive system is one that's always responsive no matter what's happening behind the scenes. So in order to do that, kind of basically, you've got 2 big characteristics. One characteristic is that the system is elastic, meaning that if you get a spike in traffic, the system can adapt and scale up to handle that. And this is one of the beautiful parts of running in something like OpenShift, is that you've got scale. You can easily manually scale up different applications, or even better, when it works the way you have auto scaling, which is great. So the applications can adapt to the load. They can scale up, they can scale down, which is great. Akka loves this kind of environment, as I'll show you in a minute. Just as importantly is the resiliency part, that when things break, and I like to use the term when, or the word when, not if. Everybody seems to say if it breaks. It's like, no, when it breaks, it's going to break. So let's just build a system that from the beginning that deals with that. And that's, again, that's fundamental to what we do with things like Akka. And so when we say lose a pod for some reason, maybe it's cut off in the network, or the machine that's running on in the cluster goes down, who cares? So we lose a pod. And this is, I think, an example of the symbiotic relationship where Kubernetes does some things as well as Akka does some things. So, and I'll be demonstrating that in a minute, but basically it's like, it's just a feature of the architecture of the application to deal with failure, to be resilient. And that really kind of comes between some of the responsibility for dealing with failures happens on the OpenShift side. Some of the responsibility for dealing with failures happens on the Akka side. So that's why I want to show you another demo that I think will be more cooperative here. Let me show this one down and show this one. So this is a demo application that's running on my laptop in code running containers, which is great for me as a developer because I have a real environment where I can run pods and do my deployments and test everything out on my own system. This demo app though has this visualization piece, and you can see it's moving around because the application, this demo application is doing stuff, and the visualization is showing it. So this is just a browser tab that's doing some pretty fun stuff. But what I'm showing is that there's a Akka cluster running, and it's running with 3 pods. So that's represented by these 3 big circles. If I go to the tab, to the console in OpenShift, this application that I just call a visualizer because its big thing is showing that information on the screen. But it's basically 3 JVMs running in containers within 3 pods right now. I'm going to scale it in a moment. And so there's 3 pods running. Now the other circles represent actors that are running in this system. So the main players are the ones on the perimeter, and these are called, these represent real things like IoT devices. So every one of these circles, as I mouse over, you can see there's kind of a little identifier. Each one has a unique identifier. So this is like for IoT device 13-11 or IoT device 32-11, that type of thing. So these are the digital twins. So as an example, if this was an IoT app, if this was a shopping cart app, one of these circles could be your shopping cart, and another one of these circles, which is an actor, representing a real actor running in this system, in this cluster right now, would be your shopping cart, my shopping cart, somebody else's shopping cart. So right now in this demo, there's about 100. They come and go. And the reason they come and go is that they're receiving messages from another simulator, which is just another Akka cluster that I set up for this demo, which is sending in HTTP requests. And that's what when I click these circles, it shows the flow of the HTTP requests coming in. These are all they're coming in through a load balancer, a load balancer set up in OpenShift. And then the requests are landing on HTTP endpoints in each of these different nodes. But then the requests are for specific entities, specific things like, say specific IoT devices. So I turned up the traffic to 2 of these members of the cluster, and you can see the HTTP request flowing into this number 46, but then you can see them kind of fan out to specific entities across the cluster. So this is messages. Some messages are going within the same JVM, which is, let me turn off the flow again to show you. This little hierarchy that falls off of this orange circle down to the green circles, down to the blue circles. There's a little hierarchy here. All of this is running in a single JVM, one of the 3 JVMs. Same thing here, another hierarchy. This is actors, they're collaborating together. So this kind of showing everything running within 3 different JVMs. So we got all this traffic flowing in, and then the messages are getting routed around the cluster as needed. Now, the green circles represent shards, and you're probably familiar with shards, like databases use shards, things like that. And shards are really used for distributing work around a cluster. So in this demo app, there's 15 shards, and I think it's 15, no, it's 18 shards. And the number of shards is fixed. So one thing I want to show you though is I want to simulate or actually do a failure. So I'm gonna kind of flag, kind of randomly pick one of these entities that turn red, and its associated shard turn red. And what I'm going to do is I'm going to stop this pod. this 46. And I can do that by just coming up and to the left and clicking, and then this pod should stop. And then we should see, now what's happening is that we were at 3 pods, now we're down to 2. And then right away, the shards got redistributed across the cluster. And if it's cooperating with me, we should see, oh, it didn't. Let me do it again. I don't know why I lost the red dot. Let me do that one more time. I'll kill 49. Kill 49. So the whole JVM goes down. All these guys go down. And then right away, this shard, we didn't even lose it. It was resurrected on another member of the Akka cluster. So what I'm trying to point out here is that in the meantime, Kubernetes OpenShift is saying, wait a minute, this service wants 3 pods. It's down to 2. Let me start up a new pod. So pretty quickly, a 3rd pod came back. But in the meantime, while things were happening external to the JVMs, internal to the JVMs in Akka, things were reacting. So like redistributing shards quickly, because Akka doesn't know if or when one of these pods is going to come back and rejoin the cluster. But the reason I flagged it was that before, this entity actor and this associated shard was on a different node. I killed that node, and as quickly as possible, the system adapted to that failure and just redistributed the load across the cluster. Now, another thing I can do is I'm going to scale up the traffic. I'm going to scale this up to 10. So what we should see is that we're going to see on the top right, as soon as those pods start up, we're going to see more traffic come in. And then the bottom, I don't know if you can see it, but on the bottom left, there's a count of the number of entities, and that number is going to go up because as I run more of these simulator pods, it's sending in more HTTP traffic, which means there's more activity, which means there's more entities running. So I'm trying to simulate like a spike in traffic. So now that that's happened, we were down around 100 or so entities, now we're up to around 174. So I'm going to go back to the dashboard, and I'm going to spin this up to, say, 5. So what we should see is back here, when those pods come up, they spin up the JVMs wake up, Akka starts running in those JVMs. It starts looking at its configuration, and it talks to Kubernetes and says, am I the only one, or is there others out there like me? And they start talking to each other over the network, and then they join the cluster. So here we go, they just popped in. So as soon as Akka sees that it's got more capacity, it's starting to move some shards over to these new members of the cluster. So it's redistributing the work. So we had a spike in traffic. So either manually or automatically, we scaled up the application, and now we're seeing the work getting distributed across the cluster. Now, all this behavior is out of the box part of Akka. And for the developer, like for me writing this demo application, I don't worry, I'm not dealing with all of this message routing and rebalancing and all that stuff. I'm really just writing the code for the business logic that goes into these entities, like my shopping cart app or my IoT app or whatever app I'm trying to build. I just write that code, and then I know that my code is resilient and scalable, elastic, all those good things. But again, there's no drama for me in doing this. It's just a feature of the way the system works. So that's kind of what I wanted to show you in here in this live demo that we scaled up, we broke some things and recovered from it and so on. So let me go back to the slide deck. So actors actors are really interesting. The concept of the actor model actually was conceived back in the 70s, back when a lot of computer science that's still in use today was conceived back in the 60s, 70s, things like that. Some of the real core cornerstone computer science concepts came out in that age. Anyways, the actor model came up then. About 10 years ago, one of the co-founders of Lightbend, Jonas Benir, brought the actor model to Java and Scala. And the actor model is pretty straightforward. A developer writes code just like they write most code. If you're a Java developer, you write classes, you write methods, functions, things like that. When you write Akka code, you do the same thing. The only difference is that actors are somewhat self-contained. They're more like people texting each other than they are like, say, one piece of software invoking a method, from one object to another object, in object-oriented types of programming. Here, the objects, which are actors, abstracted as actors, are separated by an asynchronous message environment. So the only way actors talk to each other is sending each other asynchronous messages. So I always like using the text analogy, where if you and I are texting, I text you a message. That's an asynchronous message. I'm not waiting for a response. I might want a response from you, but I don't know when I'm going to get it, if I ever get it. When you get a message from me, you may or may not respond to me. Well, that's kind of the way actors work. When I first saw this as a developer around 2013, it rocked my world, to be honest. It's why I work at Lightbend. It was like the coolest thing I ever saw as a developer. I still think it is. But anyways, it's a really interesting way to build distributed, highly concurrent systems. And the other thing I want to stress, though, is that in this demo, the last one I was showing you, I was just showing you a cluster of members in an Akka cluster where we were just doing hundreds of actors. If this darn map demo was working, I wish, there's like 200,000 actors. And, so the scale is that the actors are really, really lightweight. And I tend to think of them as microscopic, that when you're building a system, and a process like a single pod running a JVM is capable of handling tens of hundreds of thousands or even millions of actors. It's just a matter of memory and CPU, but it's still pretty economical because they're pretty lightweight. So another thing I just want to run by real quick, because this is another feature of one of the things we're very excited about in terms of doing persistence, database operations, is CQRS, or Command Query Responsibility Segregation. You may or may not have heard about it, but it's an alternative to CRUD, which is create, read, update, delete, which everybody, any developer knows CRUD. Anybody, especially any back-end developer, that's their world, is CRUD. That's been my world for decades. But there's this new way of doing it, and there's some pretty good reasons for it. But I just want to kind of give you a quick overview of what CQRS is and why it's useful. I'm not saying you use it all the time, but it's definitely something to consider. So the idea in this diagram is that on the right, say you've got a client. It could be, say, a human on some device, or it could be a mechanical thing, some IoT type of thing. But in any case, you've got something out in the real world that's talking to the backend system. And the requests, or the conversation between things in the real world and the backend system, falls into kind of two categories. The client's either asking the service to do something, which is considered to be a command, or it's asking the service to read something, which is considered to be a query. So in the case of a command, when a command comes in, the command is like an intent. Please do this. It hasn't happened yet, but you're asking the system to do something. So it goes over to what's called the write side. And on the write side, what happens is that you take that command, you validate it. If everything looks good, you run your business logic, everything's cool. So what's emitted are events, and events are historical facts, things that happened in the past. So it's like add item to shopping cart, remove item from shopping cart, change the quantity of an item in shopping cart, add shipping address, add billing address. Each one of those things is an event. The sum of all those events is the current state of your thing. Like the current state of your shopping cart are all those events run together. But the deliberately what's happening at the database level is that only the events are being written into what's called an event store, like a real simple table, basically, in a database. And it's kind of like a key value type of thing. You know, the key is like the identifier of the thing that you're changing, maybe the time or sequence number of when you did this, and then the actual contents of the change itself. So it's some kind of a state change operation. But the big thing, the reason for doing this is that it's very lightweight. Client makes a request, it comes into the system, you get processed, and all you're doing is inserting events into some table, and then you're done. Now, what about the query side though? We're responding back to the user and say, yep, we got your request, we made the change to your shopping cart or IoT device, said, hey, this happened, and we persist that, whatever, but we're responding as quickly as possible. After the fact, as these events are flowing into the system and kind of in a background process, this detached from making the user wait for these things to happen, we're not making the user wait for these things to happen. I think that's one of the biggest features of this, is that in the background, we're processing these raw events and projecting the data into views. Views that are structured for the types of queries that this, say, service has to do. So when the query requests come in, then that's what where they go, because this event store is not very queryable by design. It's really if you want to do queries, you're doing queries against these other data structures that are detached from the main flow of sending in requests to make changes. So the reason for this is things like you got a high volume application, and or maybe you have an application where it's hammered the database to a point where it just can't go any faster, and you've tried and tried and tried, and you can't get the database to go any faster because you have too much contention, too much throughput, things like that. So an alternative is the CQRS approach, because one of the things we focus on at Lightbend with things like Akka microservices is helping people build cloud native high performance applications. I think another big thing though is that the data models for the read side, actually, I think it gives you more flexibility. So for example, typically in a CRUD application, we use a good old relational database. They're great, they're powerful. We all know how to use them. They've been around for a long time. They're very mature. They're just wonderful. But it's one data model. But it could be that some of the queries you want to do are served best from relational, but other queries you may want to do with something like Elasticsearch or some other type of database. And with this approach, where you've kind of detached the flow of propagating raw event data into your queryable stores, gives you the opportunity to have, say, some of your queries are being served in a given service from relational tables, and some of the other queries are coming from something like Elasticsearch. All this stuff is being kept in sync. Now, the big thing is that there's an eventual consistency gap here, meaning that this isn't a single transaction where I insert here and then right into this, into the query structures. It's a detached transaction. I put the event in, I'm done. Back to the user, everything's good. And we're not making the user wait for all this other stuff to happen. This takes people back a bit. When people first see this processing flow, it takes a little getting used to, but and some people just can't get it. But a lot of this is getting more and more popular all the time. It's been around for a long time. We didn't invent it at Lightbend, but we like it because it's just yet another thing that works really well with actors, with Akka, where there's this concept of state, where actors are inherently stateful. So I want to show you an example of that here real quick. You often hear about building stateless systems, and they're great. I mean, it's the norm for building stateless systems, and you can scale stateless systems very nicely, and everything is great, and it's relatively straightforward for the developers to build, and it's a very mature way of doing things. I'm not saying anything bad about stateless, but it does come at a cost because there is state, and the state is in the database. So we're really delegating the responsibility for maintaining state to the database. And the way, very quickly, the way a stateless system works is that a request comes in, say, I want to add an item to my shopping cart. The stateless application needs to query the state from the database, pull it into memory, run its business logic to change it, and then write out whatever changes to the state back to the database. Then it throws the state away. That's the stateless part. So it's simple, it's straightforward, it's hard to break, but you've got this read-write cycle. Every single time a request comes in to change something, you've got to recover your state, change it, and then write the state changes back to the database. We know how to do this. We've got tons of great tools for doing this, but like I said, that the burden of responsibility for managing state is down at the database level, and sometimes it gets to the point where the data, especially when you have high volume, high performance applications where maybe the database just can't go any faster. So the alternative is this CQRS approach, and we're adding kind of the statefulness with Akka, in that when a request comes in for, say, to change my shopping cart, if the state isn't in memory, then we recover the full state from memory, by reading all those events, so, what has happened to this shopping cart in the past. But now all that state's in memory. And I like calling it hot state. It's there. So from that point on, using CQRS, every time we make a state change, all we're doing is a simple insert. That's it. Insert, insert, insert. No more queries, because the second request comes in. Yep, the state's already in memory. We're good to go. Run the business logic, insert. Another request comes in, no more query, run the business logic, do the insert, we're in. So, it's taking some of the burden of responsibility off the database, gives you more processing capacity, or throughput capacity, with maybe without putting all that responsibility on the database, and maybe choking on the database, which is often where I know applications that I worked in the past, that's typically where we ran into our performance bottlenecks, was down at the database level. So this map application, the WhereOnEarth thing, it's using CQRS, it's using Akka microservices. The first service, the simulator service, only has a journal because I don't really need to do any queries from it. The second service has a journal, and it has a view projection. And what I wanted to do, I'll go back to it, but the darn thing's not going to work for me, but it's like, imagine if you will, if this thing was working. Can't believe this has happened to me again. I've done this demo a bunch of times over the last few months, and yesterday and today is when it decides to hurt me. So normally what I would do is I would go to an area, and I'd say, I want to click. I'm going to try it again. It probably won't work, but try and create some devices here. And then there's a momentary pause in this area, and then normally I'll zoom in, and you can kind of see all the devices appear in this region. So again, imagine, if you will, these boxes are filling up. But what the data that we're looking at on this map, the point I wanted to make, and the reason I went back to it, is we're looking at the data in the view. So in order to, the latency that you would have seen if this was working when I clicked, and then you start to see stuff appear in the map, is that it was going through the gauntlet of, the request came into this service. It did a bunch of work. For every single device it was going to create, it was doing an insert into its journal. And then in turn, it was sending over, for every single device, like 1,000 devices, it was sending over 1,000 gRPC requests to the second service. It got it. All those requests got, those are state changes, like create a device and so on. They got inserted. And then all those events got processed into this view. And then we see the view on the map. And when it works, it's pretty cool, but I can't do it for you. Oh my gosh, I'm glad I'm off next week. Sorry about this. So that was a pseudo demo. So I'm pretty much done. I just wanted to kind of wrap up with and maybe while we're doing a Q&A, I'll see if I can get this app started. But the points I was trying to make in this demonstration is that when you're moving to these new environments, these cloud-like environments, OpenShift brings the cloud to on-prem is one thing. Yeah, I've worked with some of our customers where, it's like a whole new world for them. You got this beautiful Kubernetes environment that is provided by OpenShift on-prem. And I've also been at, I've met with a lot of DevOps folks, and the fun thing there with talking to you guys was, you guys have this cool environment. You're trying to convince application teams to use it, but not only use it, but use it well. Do things like that. And I think in order to use it well, they gotta, I forget the guy's name, but somebody said that the new literacy of this century is not just that you can read, but that you can learn, unlearn, and relearn. And I think that's what people have to do. That's what developers and architects have to do when they go into the cloud. If you're going to really build cloud native applications that really take advantage of the cloud, there are other ways that may hurt your head at first when you look at them to do things. And that's what we provide. Akka loves running in the cloud. It was built to run in the cloud. When this type of technology came along, it was the perfect environment for running Akka. So cloud native applications that thrive and are efficient and work well in the cloud. And these Akka clusters, just as I hope I demonstrated to you quickly, things like scaling up, scaling down, dealing with failures, and the application itself just goes, okay, cool, yeah, I expected that, and everything just works. And for the developer, it's not rocket science to do it. And it all happens because we're running in environments like OpenShift, which is just insane. So I started out with this picture with this lovely fish. They call it a clownfish. I guess it looks like a clown. I think it should have a better name than a clownfish. But started out with a symbiotic relationship in nature. But I think there's this really great symbiotic relationship between Akka clusters and OpenShift. So I think we're doing really good on time. I know. Before I go into QA, these demo apps, if you're a developer, if you know developers, they're available on GitHub. So I put the links there. There's actually both applications have two different repos. So the map app has these two repos, including the JavaScript that makes the UI work. And then this, we call it the crop circle. This circular demo app is also available. It's got two. They both are set up for running in Kubernetes environments. And I apologize in advance. I've got a massive amount of work to do on the READMEs because I'm deploying these demo apps to so many different environments and so many different databases that it's taking some time to compile all the documentation. But the READMEs, I think, are in reasonable enough shape. If somebody is interested and really wants to get these working and they run into a problem, they can certainly find me on Twitter or email me. Here's my information down here. But I'd like to thank everybody for listening in. Again, I'm going to apologize, but I'm going to try and see if I can resurrect this application, but maybe we can go into a Q&A.
Yeah, really cool stuff. Even without that demo, I hope you're able to get it working. But even if not, Hugh, that was some really interesting stuff. So thanks for that. Yeah, let's go ahead and go into the question and answer period. We've received some questions, but there is plenty of time, guys. If you have a question for Hugh, go ahead and use your GoToWebinar control panel. We'll try to get to as many as we can. Okay, so here's the first question. And I think I'm asking this one correctly. When changing on user interface, does the code also change accordingly? I think that's what he's asking, but I'm not entirely sure.
Well, I mean, this is no different than really any kind of back-end app relationship to a user interface type of app, in that usually there's some kind of protocol, RESTful JSON type of protocol between the client and the back-end service. So of course there has to be agreement on what that protocol is. What's the content and format of the data that's being exchanged, being sent in from the client to the back end and from the back end back to the client. So really, there's really no difference there.
Okay, all right. Next question here. Okay, so I want to do some proofs of concept on Red Hat OpenShift on my existing Kubernetes environment. I've seen a few docs, but in AWS is giving cloud formation to make a complete environment. Can you give me some inputs on this, how I can set it up? I'm not quite sure actually if that's for you or if that is for one of our OpenShift guys.
Well,
if
I can
it's
try.
not for you, sure, go ahead.
I'll give my part, and if feel free for anybody else. But for me, like I've run both of these demo apps. I started the development using things like code-ready containers. And if you look at code-ready containers, which is part of OpenShift, it's the OpenShift console, which is very cool, and the OpenShift and Kubernetes infrastructure to go with it, running on your laptop. So it's pretty easy to set up. I mean, you kind of need a development environment, a laptop or desktop or whatever you're using. There's a reasonable amount of CPU and memory capacity, but nothing spectacular. And you're good. I mean, you got an environment. So this visualizer demo that I was showing you is running on my laptop using OpenShift, which is in front of Kubernetes. So I've got a full-blown environment there, and scaling up pods and scaling down. And then like I said, I did all that to build these applications, get them running, and then when they were ready, then depending on what target environment you have, then you deploy them to some real environment, some cloud environment or on-prem OpenShift environment, things like that.
All right. Next question. I noticed that there is a .NET implementation of Akka as well. Is it similar in capabilities to what you've described today?
There's, I'm aware of it. I know they've parallelized themselves a bit. But to be honest, I'm not that familiar with it. But the idea is the same. It's the actor model, which is so you got that fundamental capability. It's not part of Lightbend though. It's not part of Akka is open source. It's it's an open source project. It always has been. But Lightbend, we have engineers that work for Lightbend that work on Akka. We have a very big, good sized team, very talented people and of course there's a lot of contributors out in the wild that contribute to Akka as well. But Akka.net is completely separate from us. But I think they were inspired by this Akka version.
Okay. All right, great. Next question, is there any support for neo-semantics and or GraphQL structure with Lightbend?
There's no, I don't think there's any direct support for it, but it's common to use the right tools for the right job. So say you're building a Java application, Java is just Akka is just another toolkit or framework that you're using in addition to other frameworks or toolkits, together in the same code. So we do have some plugins for handling the event store in the CQRS pattern with Akka. And some of them we maintain, some of them come from the community. I don't know if there's a GraphQL one though or not. But other than that, like just for general, like for the views, projections, I think that's perfectly doable. Where say you're taking the raw events and you want to project them into a graph database or something like that, GraphQL, then go ahead. But it wouldn't be, we're not standing in your way, I guess. You could use the other libraries, the other frameworks to do that and make it work with Akka.
Okay, all right. Okay, quick time check. We're about 6 minutes to the top of the hour. I think we have time for 2 or 3 or maybe even 4 more questions here. Let's see, next question. Which database are you using here for events persistence?
I'm using 2. One is Cassandra for the events, and I'm using Postgres for the query side, the read side.
Okay. All right, great. Next one here, for multi, e.g. 1000 IoT MQTT data stream, actors were running multi-containers. What is the best time resolution in this setup?
Wow, I'm not sure I understand the question. Can you read it to me again one more time?
Sure. For multi, and then it says e.g. 1000 IoT MQTT data stream.
Oh, I gotcha. Okay.
Okay, got it.
Yeah. I'm not using MQTT in this demo app, and I played around the communication between the two microservices. I've kind of set it up so that they can do HTTP or gRPC, and I was playing with both. The gRPC, of course, is working really well because it's got more bandwidth, because you know the level of messages between the two microservices can get pretty extreme depending on how many devices I'm trying to create. If to take it to the next level where it's like a real, and I'm a dead novice on the real IoT stuff, but to take it to the next level would say MQTT would be potentially different. But I don't know. I mean, the response times. I guess the thing is that it's easily scaling to thousands of messages per second coming in, and I've run it on fairly modest, like six pods, for example, and I've never really seen it struggle with say 2,000, 3,000, 4,000 messages per second. It's more the databases that start to struggle behind the scenes versus the messaging coming in.
All right. Okay, next question here. Let's see. How can you handle scaling bandwidth when Akka clusters are in two different regions?
Oh, Akka clusters tend to be the speed of light is slow. I've learned that now. Yeah. One thing I learned is, like the speed of light it's 186 miles per millisecond, which is kind of interesting. It's 186,000 miles per second, the speed of light. So you just divide that by 1,000 and you get 186. And I've worked in environments where we had data centers, and I actually plotted out on the map, like we had data centers in Atlanta, Houston, and Austin, and how many milliseconds apart they were. And when you I think it was between Atlanta to Texas, it was like 12 milliseconds or something like that. It's like, wow, 12 milliseconds, that's way too slow. Darn speed of light, it's just too slow. So we run into the same thing with Akka. The cluster, the members of the cluster can't get too far apart physically because they're talking to each other very intimately. I mean, they heartbeat each other. They actually in Akka they call it gossip with each other. So they're constantly gossiping with each other. All the nodes or all the members of the cluster, and they're chatting with each other to keep an eye on each other, because when say one of the members stops responding, the other members in the cluster have to react to that. Like, wait, well, we just lost that one member. What's going on? And there's all kinds of strategies for dealing with that. But so we do have some multi-data center capabilities, but it's at the data level. So if you say you have a data center in San Francisco and another data center, or like on the West Coast and the East Coast of the US, for example, then you're looking at some kind of data synchronization between those two environments, not an Akka cluster that spans those two environments, because they're too many milliseconds apart from each other.
That's kind of amazing, actually. Think about it. Okay, let's see. Okay, one more question, and then we'll close out the question and answer period. Here it is. Can you perform an eventual consistency pattern with Lightbend talking to SAP?
I don't see why not. Look, it's working. There it is. I don't know if you can see it. Darn thing.
Well, at least you got it going.
Yeah. I don't see why not, because the way the building of the view works is that the the way the APIs work is the events are fed into code that you write or I write as a developer, and we get that code, and then we are responsible then for persisting it somewhere. So as long as you have access to the APIs in, say, Java or Scala to persist to SAP, then you're golden. So it's pretty open for that. So the nice thing is, it's kind of the hard part is kind of feeding the events from the journal into your code. Well, that's handled by Akka. So the part that we handle as developers is really the processing of those events into our target database environment. So like I say, as long as you have the access to the APIs, you can make those APIs work in Java or Scala, you're good to go.
Okay. All right. Well, we are about 5 minutes to the top of the hour, so unfortunately, that is all the time that we have for question and answer period. But I do want to thank everybody who did submit questions, and if we didn't get to your questions, I apologize, but please know that the questions will be forwarded onto Lightbend, and so you will hopefully get your question answered by somebody from the organization there. Also, a quick reminder that today's event has been recorded, so if you missed any or all of the event, or if you just want to watch it again, you'll have the opportunity to do so. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And the webinar is also going to be living on the devops.com website, so you can always go look for it there. Just go to devops.com/webinars, look in the on-demand section, and it should be right there waiting for you. Okay, one last thing I did mention at the top of the hour, we would be doing a drawing for $100 Amazon gift cards. So without further ado, let's go ahead and do that. Our first winner today is Bill G. Congratulations, Bill. Our second winner today, Ray A. Congratulations, Ray. Third winner today, Linda T. Congratulations, Linda. And our fourth and final winner today is Terrence L. Congratulations, Terrence. We'll be following up with all four of you offline by email to get your Amazon gift card over to you. So please check your inbox. If you don't see something there, please check your spam folder. Hugh, thank you so much for a great presentation. Despite the demo gods not in your favor today, it was still a great demonstration and presentation. I really do appreciate your time and your expertise here.
My pleasure. Thanks for the opportunity.
All right, great. Also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I am signing off. Have a great day, everybody, and please stay safe.